What is polynomial function? I'm gonna first look into the definition of the polynomial function, and then we'll see some example. Let's assume n be a non-negative integer, and let's assume that a sub n, a sub n minus 1, a sub 2, a sub 1, a sub 0 are some of the real numbers. And let's assume that a sub n is not equal to 0. Then the function of this type is called the polynomial function of x with degree n. If you look into this definition of the polynomial function, you can see here there are actually some of the power function like x, x squared, x cube, and then so on. And then those constant that we have chosen over here, they are multiplying with those power function, and then we are adding all of these terms together, and then we are forming this type of polynomial function. The coefficient a sub n is called the leading coefficient. You can see if you look into the each of these term, there's the probably here is x to the power 0, this is x to the power n, this is x squared, and then so on. So whatever is the highest power function appearing over there, whatever is the coefficient of that, that is said to be leading coefficient. And then whatever is the high on this term which involves the highest power function, if you look at the power of that power function, like over here x to the power n, the n is said to be the degree of the polynomial. Here are a few examples given over here. You can see here we have only two terms, and then we have leading coefficient on this polynomial function is 2, and then x to the power 1 is the highest power function appearing on this function, so that is the degree of the polynomial. So we say this is the first degree polynomial, and as you notice that this is actually just a linear function. That's also we can call. And on this example of the polynomial function, we have the highest power function appearing here is x squared, so the polynomial is of the second degree, and the leading coefficient on this case is 3. In the similar way, you can look into this example where the function is defined by h of x equal to 7 times x to the power 5 minus 3 times x to the power 4 plus 10 times x squared minus 6x plus 9. And you can see here whatever is the highest power function appearing, and that is, you can notice that this is 7 times x to the power 5 is in the leading term, and 7 is the leading coefficient. The highest power function appearing here is x to the power 5, so 5 is the degree of this polynomial. So we can say this is 5th degree polynomial. No matter whatever is the polynomial function we have given, the domain will be all real number. It is because you might have noticed by the definition of the domain, we can just use that, and over here also you can see whatever is the real number we input will be always getting an output. So on that case we can say that since we are, no matter whatever real number we plug that in, we can always get the output. So on that case all of the real numbers can be in the domain of the function. You can actually also look into the graph of the polynomial function. You might have noticed here, okay, 2x minus 1 is actually just the linear function whose corresponding graph is the straight line, right? And then if you look at this quadratic function, the second degree polynomial, you can see this is like opening up or parabola. The leading coefficient will determine either it is open up or opening down, or parabola. If it is negative, the leading coefficient is negative, then it will be opening downward parabola, right? And then here is an example of the 5th degree polynomial. You can see here this is the shape of the 5th degree polynomial, and you can see here there is actually the x-intercept is somewhere over here. It is negative 1.183, and then the y-intercept is 1 on this case. Okay, now we'll try to see how to find the degree of the polynomial, x-intercept and y-intercept of the polynomial function. And these are very straightforward rules, like to find the degree, like we have said earlier that you just need to look at the highest power appearing in the polynomial function, and whatever is that, that is the degree of the polynomial. the highest power appearing on this polynomial function is 8, right? So that's why this is the 8 degree polynomial function. To find the y-intercept, you just need to do is you just evaluate this function at 0. Okay, so for example, when you evaluate this function at 0, what do you get? This will be 5 times 0 to the power 6 plus 0 to the power 4 plus 4 times 0 to the power 8 plus 10. So on that case, that will be just the 10, right? So that will be our y-intercept. To find the x-intercept, we need to solve this equation. Whatever is the polynomial function we have given, we need to set that equal to 0 and solve for x. Okay. In this example, we'll try to find the degree, x-intercept and y-intercept of the polynomial. Let's take one of the example given as f of x is equal to x squared times x plus 6 to the power cube, and our goal is to find first, let's say, degree. So how do you find the degree of this polynomial? First of all, is it a polynomial function? If we expand x cube, x plus 6 to the power cube, that means x plus 6 multiply with x plus 6 with the x multiply with x plus 6, then we get an expansion that clearly look like a polynomial. When we multiply by x squared, then still it will be a polynomial function. But how to find the degree? You can see when we expand x plus 6 to the power cube, there will be x cube is the highest power function appearing over there. When we multiply with x squared, this will be actually x to the power 5. On that case, 5 would be the highest power appearing over there. So that's why the degree of this polynomial is 5. To find the x-intercept, we set x squared times x plus 6 to the power cube is equal to 0. It's already in the factor form. You might have noticed that this will be actually equal to 0 if you can see x times x times x plus 6 times x plus 6 times x plus 6 is equal to 0. And you can clearly see that means actually how many solution we get when x equal to 0. When you set x equal to 0, we get x equal to 0 as an answer. When you set x equal to 0, we get x equal to 0 as an answer. And when you set x plus 6 equal to 0 and solve that linear equation, then what do you get? We get x plus 6 equal to 0, subtract 6 on the both sides, so we get x equal to minus 6 as a solution. Similarly, you can do the same thing, but you will get only 0 and minus 6 are the solutions of this equation. So on that case, the x-intercept are 0 and minus 6. To find the y-intercept, we just need to see where the function, what is the value of the function at 0. So that's why we just need to compute what is f of 0. So f of 0 will be, on this case, 0 squared times 0 plus 6 to the power cube, and that is just equal to 0 square is 0, multiply with anything would be 0. So that's why the y-intercept is actually equal to 0. Now we'll try to define what rational function means. When you understand what polynomial function means, to define the rational function, we just need to uh, take the take the polynomial in the numerator and a polynomial is in the denominator and form a cosine function. If on a cosine function you have a polynomial on the numerator and polynomial function on the denominator, that cosine function is said to be rational function. We just need to make sure that that denominator function is not equal to 0. Okay, and so that's how we can define the rational function. The domain of the rational function is actually the set of all real number such that the denominator is not equal to 0. We can see on this example, here are two examples of the rational function. On the first one, we have a polynomial x plus 1 is in the numerator and x squared minus x minus 6 is in the denominator. So the cosine function formed by these two functions is a rational function. But you can see here on the denominator, actually if you set it equal to 0, we get this denominator function will be equal to 0 when x equal to negative 2 and then 3. So that's why the domain of this function is set of all real number between negative infinity to negative 2, negative 2 to 3, and 3 to infinity. And the domain of this rational function will be, you can see the denominator is never equal to 0, so the domain is all real number. Let's try to see the graph of this rational function x plus 1 over x square minus x minus 6. So we can go to the Desmos calculator, and then whatever function we have, so x plus 1 divided by, so x plus 1 divided by x square minus x minus 6. So x square minus x minus 6. So you can see this is the graph of this rational function, right? So that's the exact function we have, and then you can clearly see that on this graph, no matter how much you zoom in, the domain would be set of all real number from negative infinity to somewhere over here, and then from this location to that, and then from here to infinity, exactly somewhere at, probably at, what was that, at -2. Let's try to zoom out and then see if that's the exact at -2. Whenever x gets closer and closer to -2, the curve just gets smaller and smaller from the left hand side, and when x gets closer and closer to -2 from the right side, the curve is just getting larger and larger. Exactly at -2, there is no value of the function. On that case, we can say the function is not defined. Similar type of interpretation we can do here at 3. So that's why -2 and 3 are not in the domain of this function. Alright, now we will define what vertical asymptote means. Let me first show you one example. It is given a rational function whose graph is given over there. Here, no matter how much you zoom out, you can see here this curve is actually this rational function. It's whenever this curve is getting closer and closer to somewhere around this location, the y values or this function is just getting smaller and smaller from the, and whenever we go closer and closer to that location from the right side, the curve is just getting larger and larger, right? So let's, if you want to look into what that location is, this look like at x equal to -2. So we have some interesting feature here. So the vertical asymptote is actually the line x equal to a is said to be the vertical asymptote for the graph of the function if f of x either increases or decreases without bound as x approaches a from either the left or the right. So that's exactly same situation we are having here, right? When like let's assume x equal to -2 is one of the straight line here. I can construct that if you want to look into the graph. So we have this function x, we have this line x equal to -2, this vertical line, but you can see here whenever we go closer and closer to that line from the left hand side, this function is just getting smaller and smaller, or it's decreasing without any bound, right? You can see here, if you zoom out, you can see it's just getting smaller and smaller. At the same time, whenever we go closer and closer to -2 or closer and closer to this straight line from the right hand side, the curve is just getting larger and larger. So either, I mean, it was just sufficient, the left hand side issue, to be this straight line x equal to -2 is a vertical line, but I mean, either you go closer and closer to -2 from the right side, the same type of phenomena, the curve is getting larger and larger without any bound. So this is clearly a vertical asymptote. Can you show me what is the another vertical asymptote on this for this function? All right, yes, you might have noticed somewhere over here on this location when x is x equal to, let's say, 3, we can clearly see here, even on this location, whenever we go closer and closer to 3 from the left hand side, the curve is just getting smaller and smaller. It's decreasing without bound, right? So that's why it's actually the line x equal to 3 is said to be vertical asymptote. So this is a nice example. You want to see some more example? Let me see if I have some over here. All right, let me first so this is the curve, the rational function y equal to 5x plus 2 divided by 6x square minus x minus 2. We can see the similar phenomena over here at x equal to -2, right? And then also at x equal to 2/3. Generally, to represent the vertical asymptote, we use the dash line, so this is the perfect image for that. This particular page, we'll try to learn how to determine the vertical asymptote of the rational function. We have already seen in the graph how to do that, right? But how to do it algebraically, let's try to discuss on that. Let's try to consider a rational function. Whenever we have a rational function, that means we have a polynomial on the numerator, a polynomial on the denominator. Let us say assume the polynomial on the numerator by n and the polynomial in the denominator by d. So how do you find the vertical asymptote for this rational function? What we do here is, first of all, we try to see if they have some real zeros in common. Okay, if they don't have any real zeros in common, you just have to do is look into the denominator and then see if the denominator is equal to 0 at some location. Whatever is the location corresponding to that location, whatever is the vertical line you have, that is said to be vertical asymptote. Okay, that's how we say if the numerator and denominator polynomial have no real zeros in common, then if you have a real number where the denominator is 0, then the line x equal to that real number is a vertical asymptote of the graph f. So you can see on this particular example, the denominator function is 0 at the denominator polynomial will be 0 at x equal to -2, right? So that's why we have seen even on the graph x equal to -2 is actually the vertical asymptote. If you have, let's say, the numerator and denominator have some like a common real zeros, that means wherever the denominator is 0, if the numerator is also 0 exactly at that location, just try to cancel out the common linear factors, whatever is that. I believe you can cancel out the common linear factor. That's why you are getting those real zeros. And then when you cancel out the common linear factor, then what you have to just do is, go to the case 1, because after you cancel out the common linear factors, then uh, there will be no real zero in common, and then you can immediately apply the case 1. All right, now let's try to see how to find the equation of any vertical asymptote. Find the equation of any vertical asymptote. And let me take one example. Let's say f of x is equal to x minus 3 over x plus 3. So how to find the equation of any vertical asymptote that may have for this rational function? As we have discussed earlier, to find the vertical asymptote of the rational function, first of all we can check if they have any real zero in common. We can see on this rational function the denominator polynomial has a linear factor, just the x plus 3, and the numerator is x minus 3. So that the denominator will be 0 at whenever x plus 3 is equal to 0. That means when x is equal to -3. But if you plug that number into the numerator, you can see that the numerator is actually not equal to 0. So in that case, they don't have any real 0 in common. So if that is the case, then we can clearly say that x equal to -3 is the vertical asymptote for this problem. Very easy, right, in this case. So let's try to see another example where we have f of x is equal to x square plus 1 divided by x square minus 1 times x square minus 9. And our goal is to find the vertical asymptote of this rational function. So how to find the rational function, how to find the vertical asymptote of these? Again, we begin from the denominator. You can see on the denominator we have x square minus 1 times x square minus 9 is equal, let's set it equal to 0 first. We want to see where the denominator is 0 first, right? And x square minus 1 has a factor x plus 1 times x minus 1, right? Similarly, x square minus 9 has x plus 3, x minus 3 are the linear factors. Set 8 equal to 0, and you can clearly see when x plus 1 is set it equal to 0, then we get x equal to minus 1 as a solution. From here we get x equal to 1 as a solution. From here, when x plus 3 equal to 0, we get x equal to minus 3 as a solution, and when x minus 3 equal to 0, x equal to 3 is the solution. So we have these four number where the denominator is 0, but if you plug all of these number in to the numerator, you can see that still the numerator is not 0, right? Negative 1 square is positive 1, so positive 1 plus 1 would be 2. 1 plug that in, you will not get 0. So in this case also the numerator and denominator does not have any real 0 in common. So that case we have x equal to minus 1, x equal to 1, x equal to minus 3, x equal to 3. All of these are vertical asymptote for this function, vertical asymptotes of the given function f of x. All right, let's take one more example, and let's take function f of x is equal to x square minus x minus 6 divided by x square minus 3x minus 10. All right, let's try to see the denominator function x square minus 3x minus 10. See if this is equal to 0 at some location. This is quadratic equation, so either you can use the quadratic formula or just factor it out up to the linear factor, right? So let me try to factor these. So I have x square, so x and x I can write down as a first term of this factor, and at the end I have negative 10, and on the middle I have negative 3. So try to think of two numbers whose product is negative 10, but when you combine you get negative 3. Can you think of that? Okay, so negative 5 and positive 2, right? So negative 5 times 2, if you multiply you get negative 10, but when we combine we get negative 3, right? So let's set this equal to 0, then we have the linear factor. When you set x minus 5 equal to 0, we get 5 x equal to 5 as a solution. When you set x plus 2 equal to 0, we get x minus 2 equal to 0, right? So that these are the two solutions. But let's try to see when you plug this number into the numerator and see if the numerator is 0. Alright, so I just want to try that. So let me plug 5 in, so I get 5 square minus 5 minus 6. So 5 square is 25, minus 5 is 20, 20. So this is not equal to 0 over there. But when I plug in negative 2, let's see, square of negative 2 minus negative 2 minus 6. Square of negative 2 is 4, right? And so this is 4. Negative negative 2 will be positive 2 minus 6. Wow, so this is actually, then it's look like this is equal to 0. So when x equal to minus 2, the numerator is 0. That means they have actually 0 factor in common. Well, what is that one? So we know that if we factor the numerator and denominator, the denominator will be x minus 5, x plus 2, as we have done earlier. The numerator can be also factored, and we already see one of the factor is actually x plus 2. Or if you want, you can just factor out like normally, this is x, that is x, and at the end we have negative 6. Try to think of two numbers whose product is negative 6. When we combine, see if those number would get negative 1, and clearly you can see that that would be x minus 3, x plus 2. On that case, you can see they have the 0 one linear factor in common. Let's cancel that out, and the remaining factors is x minus 3 over x minus 5. And you can see the denominator function will be 0 when x equal to 5, and now they don't have any real zeros is in common. So on that case, x equal to 5 is the vertical asymptote of this given function f of x. All right, now we will learn what horizontal asymptote mean. The line y equal to b, that means the horizontal line y equal to b is said to be horizontal asymptote of the graph of a function if f of x approaches b as x increases or decreases without bound. What does it mean by that? Let's try to see on this example. So I have a function here. This is again a rational function where a polynomial we have in the numerator, and then 4x squared plus 1 is in the denominator, right? So, and then this is the graph of that. You can see I have a straight line here, y equal to 0, that dashed line. Whenever you can see here, whenever x is getting larger and larger, the function is actually getting closer and closer to that line, right? So over here you can see that line y equal to 0. Whenever x is getting smaller, x is getting smaller and smaller, we have this similar type of behavior. I mean, only one, it's already sufficient for this line to be horizontal asymptote from the right hand side type of phenomena. But you can see here, even when x is getting smaller and smaller, the value is getting closer and closer to 0, and then like getting closer and closer to 0, right? So that's why this is clearly the horizontal asymptote. Now we'll try to learn how to determine horizontal asymptote of a rational function. So let's consider a rational function, right? The numerator polynomial is represented by n of x. The denominator polynomial is represented by d of x. Our goal is just now to see how to find the how to determine the horizontal asymptote, and it's very easy. What you just need to know is how to find the degree of the numerator and denominator polynomial and just compare that. So if the degree of the numerator, whatever is that, if that is less than the degree of the denominator, then y equal to 0 is the horizontal asymptote. The nice example is this one, right? So you can see the degree of the numerator is 1, the degree of the denominator is 2, 1 is less than 2, so clearly y equal to 0 is the horizontal asymptote. Done. If the degree of the numerator is equal to the degree of the denominator, right, so in that case we have whatever is the leading coefficient of the numerator polynomial, whatever is the leading coefficient of the denominator polynomial, just take a ratio of that, and y equal to that ratio will be the horizontal asymptote. For example, you can see here we have a numerator polynomial 3x squared plus 3x minus 6 whose degree is second. The denominator polynomial also has the same degree, so in that case 3 over 2 is the ratio of the leading coefficient. So y equal to 3 over 2 will be the horizontal asymptote. Do you want to check that? Okay, let's go ahead and then do that on the Desmos. Y is equal to, what was the polynomial on the numerator? 3x squared plus 3x minus 6. 3x squared plus, what was that? 3x minus 6. So 3x minus 6, and then divided by, what is the polynomial on the denominator? 2x squared minus 2. 2x squared minus 2. What did I say earlier? To find the horizontal asymptote, we just need to look into the degree, and if they are same, like say this is second degree polynomial, this is second degree polynomial, so we just take a ratio of the leading coefficient, which on this case is 3 over 2. So y equal to 3 over 2, whatever line is that, I'm gonna draw this line in a dashed line, so you can clearly see that dashed line is actually the horizontal asymptote. That's exactly we are seeing here also on the graph. All right, the third case is if the degree of the numerator is greater than the degree of the denominator, then there will be actually no horizontal asymptote. All right, let's find the equation of the horizontal asymptote. Let's take one example where we have f of x is equal to 5x cubed plus 2x minus 3 divided by 6x cubed minus 7x plus 1. So our goal is to find the equation of the horizontal asymptote. As we have discussed earlier, to find the horizontal equation of the horizontal asymptote, we need to check the degree of the numerator polynomial and the degree of the denominator polynomial. we can clearly see that the degree of the numerator polynomial is 3, the degree of the denominator polynomial is also 3. On that case they are same, right? So degree of the numerator polynomial is equal to the degree of the denominator. So if we have that, then y equal to whatever is the ratio of the leading coefficient, which is, what is the leading coefficient of the numerator polynomial? 5. What is the leading coefficient of the denominator polynomial? 6. So 5/6 is the ratio of those leading coefficients. So y equal to 5/6 is the horizontal asymptote then. All right. Okay, so now let's try to take another example where we have a function f of x is equal to x to the power 4 plus 2x square plus 1 divided by 1 minus x to the power 5. We do the same thing, check the degree of the numerator polynomial, check the degree of the denominator polynomial. And you can see here is 4 on the numerator, that is the degree of the numerator polynomial. The degree of the denominator is 5. So 4 is less than 5. On that case, what will happen? Then only y equal to 0 is the horizontal asymptote. So if the degree of the numerator is less than degree of the denominator, then y equal to 0 is the horizontal asymptote. Okay, let's take one more example. Well, let's assume we have a function f of x is equal to x square plus 6x plus 1 divided by x minus 5. What is happening here? The degree of the numerator polynomial is 2 and the degree of the denominator polynomial is 1. So 2 is greater than 1. On that case, degree of the numerator is greater than the degree of the denominator. So then we don't have no horizontal asymptote. So we write down no horizontal asymptote. Okay.